In this video, we're going to talk about the Schrödinger equation. We'll first start by showing the one-dimensional Schrödinger equation, and then talking briefly about how Schrödinger derived this equation. Now, it's important to remember that from the modern physics that we talked about in the last video, it was necessary to have a wave equation that explained how particles move. And this is where we have Schrödinger's contribution. So the one-dimensional Schrödinger equation is very simple, and here it is. I will explain all the parts in just a minute. First, we start just by writing it down. So it's I, which is the square root of -1, h bar, Planck's constant, times the partial derivative of a wave function with respect to time, psi, is equal to minus h bar squared over 2m times the second partial of psi with respect to x squared. And then you have to add plus v and psi again. Now, what are these components? Well, the wave function psi is a function of position and time in this one-dimensional wave equation. If it were a three-dimensional wave equation, it would be a little bit more complicated, but not much. And it's a function of time and space. The potential here, V, is a potential. That's the potential under which the particle is subjected to. We can look at this equation as an expression of conservation of energy. If we look at the individual terms, we can see that the individual terms are, on the left side, the total energy, IH bar partial of psi with respect to the time, is the total energy. On the right side, we have the first term, which is a kinetic energy, and we'll see this further on as exactly why this is, minus h bar squared over 2m, partial squared with psi with respect to x squared is the kinetic energy. And the final term is the potential energy. So v psi is equal to the potential energy. So Schrödinger's wave equation was not the only formulation of quantum mechanics that was developed in that period. Should have a not there. There were other ones. There was matrix mechanics, which was worked out in parallel by Heisenberg, Born, and Pascual. And then later, relativistic approaches were developed by Dirac and Pauli. However, Schrödinger's equation and this wave mechanics is a really good place to start, and it still works very well. It's a very successful theory, and that's why we're going to spend a lot of time with it. Now, how did Schrödinger derive this equation? Right? Because this is not the same as a wave equation for a traveling wave like electromagnetic radiation. So I have a quote here from Richard Feynman. Let me read it. When Schrödinger first wrote it down, he gave a kind of derivation based on some heuristic arguments and some brilliant intuitive guesses. Some of the arguments he used even were false, but that does not matter. The only important thing is that the ultimate equation gives a correct description of nature. And this is Richard Feynman. So in fact, Schrödinger basically used his intuition to generate this equation. So Schrödinger was inspired by wave optics. He started with the wave equation for electromagnetic radiation. We've all seen this. It says that the electric field has to, for a traveling wave, has to follow this equation, this second order equation, in time and space, right? So one-dimensional electric field, 0 is equal to the second derivative of the electric field with respect to space, minus 1 over c squared times the second derivative of the electric field with respect to time. And that's the wave equation for an electric field. If you start with a solution, this solution to this is a electric field that depends on x and t. It has an amplitude e sub 0, and then it's a traveling wave. Remember, kx minus omega t, anything that has a dependence kx minus omega t is a traveling wave. And in this case, it's e to the I kx minus omega t. So this is a sum of sines and cosines, right? But it's a nice compact form that we can use complex exponential. If we take the derivatives of these two and substitute in to the wave equation, we get the following. So on the left side we have 0. On the right side we have the second derivative of with respect to space gives me a k squared, I squared k squared, but that means minus k squared. So we get a minus k squared. The second derivative with respect to time gives me an minus I omega quantity squared, but there's a minus sign here, so that flips a sign, and we get minus omega squared over c squared. So we get quantity minus k squared plus omega squared over c squared times the wave function back again, e sub 0, e to the I times kx minus omega t. So this gives, the result of this means that if this has to be 0, then this quantity must be 0, and that's called the dispersion relation for photons. And the dispersion relation for photons, we'll talk about this later on as well, says that the momentum or the wave number is equal to omega divided by the speed of light. Or the energy, to be distinguished from the electric field, I have a script E, is equal to the momentum times c. So this works for photons, for light. And we know that photons act like particles, so this is the wave equation for a relativistic massless particle. Photons travel at the speed of light, they have no mass. But when you have a non-relativistic particle with mass, you have to start with a different dispersion relation. So the dispersion relation for non-relativistic particle has to be consistent with classical energy. This is the notion that Schrödinger had. And what is that? That means that the classical energy, E, is equal to p squared over 2m, right? So that's momentum squared divided by 2m. And that has to be equal to the energy of that particle in terms of its wave, its frequency. In this case, instead of h nu, we use h bar omega, same thing. This is from de Broglie's relation. Now, if you take de Broglie's relation, you can now realize that P is h bar k. And so if I substitute in for p squared, I get that h bar squared k squared over 2m, which is this term here, is equal to h bar omega. And this is now the definition of the dispersion relation which we need for a relativistic mass particle with mass. So we need a wave equation which gives a dispersion relation when applied to a traveling wave. Let's assume that our plane wave, we have a plane wave as a wave function, as a function of x and t, has an amplitude, and then has e to the I kx minus omega t. It's a traveling wave. So this is a plane wave, matter wave. If I realize that I only get 1 power of h bar of omega here, then the time derivative must be a single derivative, not a double, not a second derivative. Whereas I get k twice, I get k squared, so the spatial derivative must be a second derivative. And this leads to the notion that you have IH bar over partial with respect to t of my wave function is equal to minus h bar squared over 2m, which are the constants here in front, times the second derivative with respect to space of psi of x and t. Now, why do we have an IH bar? Because we're going to get an I out from our first derivative here. We get a minus I omega. And so if we have minus I omega here, and we need to turn it into h bar omega, we need to have an extra I here. That cancels the minus sign when you have I squared. On the right side, there has to be a minus sign here because you got to get h bar squared k squared over 2m, and when you take the second derivative, you'll get an I squared, which gives you a minus 1. So if you have a minus sign here, this turns positive. Now, if you add a potential, v of x, then you can just have v of x plus psi times psi of x and t. And this is now the derivation of the Schrödinger equation.